on reverse mathematics.
Thanks, Eric. What I'm going to talk about today is first, I really want to talk about some motivations on why we study reverse mathematics of these lower bounds, because I feel this hasn't received enough attention yet, and even among lower bound provers. And I think there are some very good motivation for studying them, but they are not obvious, I would say. So I want to talk about the motivations for, I don't know, some time. And then during the motivation, I think I'll say some very informal and very weak phrases like this lower bound needs this reasoning power to prove, or this lower bound is as hard as that lower bound. And maybe that will confuse some of you, but in the second part, I hope I will like make this a little bit more precise. I will define how it means by saying that this lower bound, let's say, requires this reasoning power to prove, or this lower bound is equivalent to that lower bound, things like that. And then we'll have our main course. After the main course, if time permits, we'll have some desserts. Mm-hmm. Uh, I I want to cook the main course really slowly. So if you have any questions, please just ask. I don't think time will be any problem. I was even worried if I will spend like only 90 minutes, but so just ask questions. And I also want to say that I think the techniques in the main course are not so difficult, so you should be able to understand it. And if you don't, then it's probably my mistake, probably not yours. So please do ask questions when there's any confusion. Uh, why do we study reverse mathematics of complex lower bounds? If I'm only allowed to answer 6 words, then I'll say this, because lower bounds are hard to prove. Just to make sure we are on the same page, let me kind of review some of the state-of-the-art lower bounds and tell you that they are indeed very hard to prove. For circular bounds, our dream goal is to show that SAT, or your favorite NP-complete problem, doesn't have polynomial-sized circuits. But we are very far from that. The best circular bounds we can prove so far is just something slightly above 3n. And that's already, I think, 30 or 40 pages long of case analysis. So people really worked very hard, and they can only slightly break the 3n barrier. Even for, I think the techniques behind these papers are not believed to be able to prove like 10n size lower bounds. So it's a really long-standing open problem whether you can prove a circular bound of 10n size. And this is not known even for the gigantic class of exponential time with NP oracle. For proof lower bounds, the situation is quite similar. In proof complexity, we have proof systems. In this talk, just understand it as some informal notion of proof systems which given a theorem and a proof and decides whether the proof is correct. And for some standard or well-studied proof systems, we would like to prove it requires, let's say, superpolynomial sites to prove some theorems. And we are also stuck on this front. We can prove an omega n square lower bound, but I claim that it's trivial. I'll give you what the lower bound looks like. Hopefully this convinces you that it's trivial. And that's basically what we know about on the most general circuit class and let's say most general proof systems or most standard proof systems. And not only do we know that we appear to be enabled to prove strong lower bounds, we actually have so-called barrier results. So towards the road of proving strong lower bounds, we have identified quite a few barriers, and each barrier is saying this or that class of proof methods cannot resolve the lower bound you want to resolve. For example, the relativization barrier says that any relativizing technique cannot resolve the P versus NP question. And roughly speaking, relativizing techniques are those techniques that treat your Turing machine or circuit as just an oracle and do not attempt to analyze what's inside the Turing machine or the circuit. And we already have quite a few non-relativizing techniques, and I think some people might just believe that the relativization barrier is not relevant anymore. I don't know. For example, the most famous one I think is IP equal to P space, and in some sense, I would also say that the whole area of circuit complexity was born in need of non-relativizing techniques. Because you really want to look inside a circuit and analyze it and see what's going on inside the circuit. So if you have any way of doing circuit analysis, then it is inherently non-relativizing. Then, in the pursuit of circuit complexity, we encounter the natural proof barrier, which says any natural proof cannot prove, let's say, P not equal to NP. And here, natural proof has a precise meaning. There's a precise definition of what proofs are natural, but it's not relevant for this talk. What I want to say is that the natural proof barriers are also can also be overcome using simple methods. For example, even diagonalization would lower bounds proof by diagonalization doesn't naturalize, if you know what that means. And there's also a recent phenomenon of hardness magnification. It basically says that even if your proof method is natural, it can be made non-natural by just a little bit more manipulation. So it's questions like how strong or how relevant the natural proof barrier really is. And finally, we also know there are, for example, the KRW conjecture is inherently non-natural. They are just proving lower bounds for specific functions. If you know what natural proof means, then you know that this is not natural. So the picture is like we have quite a few technical barriers. They are quite helpful for the practitioners of complexity lower bounds. Like they tell you what to not do, what to not waste your time on. But each of the barriers can be overcome by certain techniques. And if you are an optimist, then you might hope maybe someday someone will come up with a very clever combination of all these techniques, and they overcome all the barriers together. And by combining them in the right way, maybe you can just prove the breakthrough lower bound. But I guess I'm more pessimistic, and my take on these things is that these barriers don't capture the whole picture of proving lower bounds. And maybe they are just the first of a large series of barriers that we need to overcome in order to prove good lower bounds. And we really don't know what's behind these things. Okay, so anyway, I don't know. I classify myself as pessimist. So my personal opinion is that we don't really understand why the lower bounds are hard to prove. And here it's a maybe more controversial opinion. We already know that lower bounds are hard to prove, and we also universally acknowledge that they are hard. I think most of us don't expect that P versus NP will be resolved in the next 50 years. But I still want to say that we are still drastically underestimating the difficulty of proving strong lower bounds. like partly because we don't understand why they are hard. We only scratch the surface that these lower bounds are hard to prove. This led to the study of provability of lower bounds, let's say in weak theories. Pioneers like Rasborov and Krajcek and others, they study the unprovability of complexity lower bounds in weak systems. Just give you some taste of what the results are. We know some weak lower bounds. Sorry. Okay. We know some weak lower bounds where we already know how to prove. We also know they are provable in weak theories. And some very strong lower bounds, such as strengthenings of NP not equal to co-NP, we know that they are not provable in so-called polynomial time reasoning, or PV. And I want to say that this is really a kind of big strengthening of NP not equal to co-NP. You need to strengthen it in several technical aspects, such as allowing sub-exponential time and so on. But for the Holy Grail question that we really care about, Rasborov showed that they are unprovable in very weak theories. This is a good result, but the theory is so weak so that I don't think it's kind of relevant to the practice of lower bound provers. And in general, this remains a big open question. So just like we don't know why lower bounds are hard, we also don't know why it's hard to prove that lower bounds are hard. This brings to the topic I want to talk about today. That is, if we don't know how to prove the lower bounds are hard, can we at least classify them into, let's say, classes and say that this lower bound it's equivalent to that lower bound in terms of how much reasoning power you need to prove. And for example, one way of doing this is by reverse mathematics. For example, we normally use axioms to derive theorems, but to show that some axioms are necessary for the theorems, we assume the theorem and try to derive the axiom back. We will have a concrete example later. I also want to say that this is conceptually kind of similar to NP completeness. Suppose you have a hard problem and you want to prove it's hard. But if your hard problem is in NP, then proving it's hard would separate P from NP, so we really don't know how to do it. But if you can show the hard problem it's NP complete, or maybe complete for some other natural complexity class, then this should be treated as evidence that the problem is not in P. And this has been very successful, and I would say much more successful than unconditional lower bounds. And I guess the story here is similar. We want to group lower bounds into like equivalence classes and see what lower bounds are equivalent to what axioms. The next thing I want to talk about is why is it interesting to consider reverse mathematics of non-lower bounds. Our goal is to consider reverse mathematics of lower bounds like SAT requires super polyset circuits, which we don't know how to prove. But well, first, currently we can only study the reverse mathematics of lower bounds that we have already proved. But I think there's more things to say about reverse mathematics of non-lower bounds that makes them interesting. The first is that by investigating the provability of these non-lower bounds, it already reveals several interesting phenomena. And I guess even if you proved many lower bounds, if you have never thought about this in the reverse mathematics angle, you might still be unaware of these phenomena. And second is, of course, that observing these phenomena for weak lower bounds will allow us to speculate on stronger or unproved lower bounds. So let me give you two of the phenomena that I want to talk about. The first one, I want to talk about this today. The first one is that some lower bounds are just classical combinatorial principles in disguise. What do I mean by this? For example, the main course we will talk about later is a classic and a well-known lower bound against the one-tip Turing machines. And turns out that this lower bound is equivalent to some version of pigeonhole principle. And this was one of the results in the beautiful paper of Chen Li and Oliveira. And the title is simply Reverse Mathematics of Complex Lower Bounds. So I've stolen their title in my talk. In their paper, they considered quite a few lower bounds against one-tip Turing machines and the communication complexity and so on. And they grouped these lower bounds into equivalence classes. As you can see, there are three main equivalence classes. And I'm going to talk about, I think, this one here. Given that some weak lower bounds are equivalent to mathematical principles that we all know, maybe one can speculate that strong lower bounds like set across superpolysized circuits are also equivalent to some combinatorial principle. And first, if that's indeed the case, what kind of combinatorial principle would it be? I guess the current mathematics might have not scratched the surface of such a combinatorial principle yet. That's my pessimistic guess. And if this is not true, like if such lower bounds are not equivalent to any natural combinatorial principle, then why would it be the case? I think these are very interesting and very difficult problems to study. This is for the first phenomenon, and the second phenomenon I'll talk about in the next week is that there is some minimum reasoning required for analyzing your favorite computational model. In the next week, I'll take the resolution proof system as an example. This is really perhaps I can say the most well-studied proof system in proof complexity. And people really study it for a lot of motivations, including set solving and query complexity, TFNP, and so on. And this is also a weak proof system. We understand it. We can prove a lot of lower bounds for it. For example, this system requires exponential size to prove the pigeonhole principle. In an upcoming paper with Jiawei Li and Yuhao Li, we proved that there is a certain theory, for now let me call it T, so that you will need T reasoning in order to prove lower bounds for resolution. And let me emphasize two interesting aspects of this theorem. I'm not going into what is T, but in the next week, I hope you will understand what this T is. Let me emphasize 2 points of the theorem. The first is that this is really an intrinsic property of resolution, and it doesn't matter like what lower bound you are proving. So proving that resolution cannot prove pigeonhole principle efficiently will require T reasoning. But maybe you don't like the pigeonhole principle, so you change it to another principle, and you try to prove resolution cannot prove that. This still requires T reasoning. And our proof really doesn't depend on the hard tautology. It just requires it to be a tautology that is hard. And second, T is strictly stronger than resolution itself. I think it should be expected that you need at least the power of resolution itself in order to prove resolution lower bounds. But it turns out that this thing is, in some precise sense, strictly stronger. So let's speculate again. Pick your favorite computational model. And there is some minimal model that's needed for proving lower bounds for your favorite computational model. And at least in the case of resolution, this minimal model is strictly stronger than your favorite computational model itself. And maybe we can at least speculate this is also true for stronger models. For example, if you want to prove circular bounds for general unrestricted circuits, what's the minimal reasoning that you need in order to prove such lower bounds? And it seems quite natural to conjecture that they are strictly stronger than polytime reasoning. And is this true, and why? I feel this is also a kind of important but difficult question to study.
Defining this notion of reasoning, this will happen next week, or?
Oh, this will happen in the next slide.
Oh.
Okay, so how should we talk about this lower bound can be proved in this, and this lower bound is harder than this? I have a short answer and a long answer. The short answer is to just look at something that I call refilter problems. Suppose we have a lower bound. For this talk, let me only consider circular lower bounds, but next talk we'll go into proof lower bounds. So a lower bound says that any circuit C from some circuit class, if it has size at most some number S, then it cannot compute some language L. You can write it in an equivalent way. If you have such a circuit C in this class and its size is as most S, then there is a bad instance X on which your circuit fails to compute L. Naturally, this corresponds to a total search problem, which we will call the refilter problem for the lower bound. It is what you think it is. The input is a small circuit claiming to compute L, and your task is to refute it. You need to output some instance X such that Cx is not equal to Lx. Is this clear?
It's not described in it's like
Yeah, L is fixed. Oh, by the way, how many of you are familiar with TFNP? Total NP search problems.
Potentially there could be other ways to refute saving circuit.
Yeah. For example, actually many lower bounds are proved in more complicated way. And this will usually mean that there's at least no obviously efficient algorithm for the refilter problem. So we are really studying the complexity of this refilter problem. Actually, that's the next button. I'm asserting, I'll justify this later. I'm asserting that the logical complexity of proving your favorite lower bound is related or even equivalent to the computational complexity of the refilter problem.
Second part is well defined. The first part, I don't know how it's defined.
Maybe maybe wait for a few slides.
So for known lower bounds, you're saying that this refilter problem tends to be efficiently solvable?
Well, there are some caveats. I hope I'll also get into that later.
But broadly that is broadly that is the message.
Well, actually, the main course that we'll talk about is a refilter problem which happens to be equivalent to PWPP, if you know what that is. And we don't believe that PWPP is efficient. Like we believe it's hard. But there are also some other lower bounds where, in some sense, there is efficient algorithms for refuter, in the sense that the lower bound, the refuter problem is in TF-ZPP. I'll get into that. It's quite subtle, I would say. For example, well, this allows you to study logic questions purely in terms of computational complexity. Like I want to understand how hard is this lower bound. Then you write down the refuter problem and you ask the computational complexity of this refuter problem.
Are you defining the logical complexity as this?
I need to justify this equivalence.
The title of this slide is short answer or beautiful. What's the question for which this is a short answer?
How do we talk about the probability and the reverse mathematics?
The insight is the refuter problem.
Well, yes, this allows you to like study these problems purely in terms of computational complexity.
This is just a definition, right? Like you choose your favorite measure of computational complexity, number of steps, space, whatever you and then you're saying like when I say this lower bound is harder than this, it just means that this algorithm search problem is harder than this.
Actually, you can think in terms of reducibility, like for example, this lower bound follows from that lower bound. This means this refuter problem reduces to that refuter problem.
But the reduction also sits in some class, right?
Let's say deterministic polytime.
Like my only reservation, but maybe it's in this to be justified. But when we think about like logical complexity, we usually don't think in these terms. So maybe
don't think in these terms. What do you mean?
I don't know.
Yeah, maybe it's in this to be justified. And in fact, you can say that some lower bound is no harder than some other lower bound to prove. Actually, in the last slide, there will be a theorem saying that this is equivalent to the refuter problem reduced to that refuter problem. And the notion of no harder than and like the notion of reduction depends on the notion of no harder than. For example, if you can invoke just the lower bound once to prove your lower bound, then this is a mapping reduction. And if you need to invoke it many times, then it's a Turing reduction. And
suppose I have a proof for one lower bound and I get the corollary another lower bound. Like, is this in some precise sense going to tell me that there is a reduction between these two?
Yes, of course, depends on how hard it is to prove the corollary. For example, if you can prove it in TPV, then this is exactly saying something called TPV, PV plus true universal sentences. If you can prove the corollary in this theory, then this is exactly saying you have a reduction from this refuter problem to that refuter problem. Let me just give you some examples. So I'm just throwing more questions for you to think about. These are questions that I don't know how to analyze. For example, how many of you, well, I think this is a classic theorem, so many of you should know about this, right? Okay. There's some circuit class called AC02. For this talk, it's not so important to understand the detail of this class, but this is one of the frontier classes for which we can prove strong lower bounds. So Rasborov and Smolensky proved that polysize AC02 circuits cannot compute the majority function. You can define the refuter problem. For example, I give you an AC02 circuit that is too small to compute majority function. And you need to output an instance X such that the circuit fails to compute majority on this particular instance. What's the complexity of this problem? And for the next example, it's not necessary to restrict on the lower bounds that we know how to prove, right? So you can also consider lower bounds that we don't know how to prove, but maybe we believe it's true for some reason. For example, that we conjecture that there's no small circuit for solving SAT. So the refuter problem becomes, I give you a small circuit that claims to have solved SAT, and I want you to output a SAT instance for which the circuit fails to solve it. Well, there's a small caveat that this problem is not in TFNP. I'm not saying that defining it in TFNP would be better than defining it, let's say, just in the second level of hierarchy. But in the particular case of small circuit for SAT, you can actually use search to decision reduction for SAT to define a TFNP problem that kind of captures the hardness of proving this. So using search to decision reduction, you can you can instead consider the complexity of search SAT. The input is a circuit of let's say polynomial size that claims to solve search SAT. So given a formula phi, it should output either phi is unsatisfiable or a satisfiable assignment of phi. And then to solve this problem, your output should be a SAT instance phi and an assignment A. The purpose of A is to prove that phi is satisfiable. And what you really want is that given phi, your circuit C fails to output a satisfying assignment. Is this definition clear?
What is your goal, to find A or to find?
To find phi and A. So my goal is actually to find phi so that C phi fails to output a satisfying assignment on phi. But I also need some A to certify that phi is actually satisfiable. And that's it. Any questions anymore?
These are equivalent, I mean, maybe up to the end to the 100.
I actually don't know because the first one is only in TF sigma 2. If you know what that means. Means total search problems or verification needs an NP oracle. So I'm not really sure if they're equivalent. Maybe I don't know, maybe they're equivalent in boundary arithmetic. I haven't worked out the details.
Is there a verification? What's the problem? Why isn't it in TFNP?
Because you need to verify C of phi is not equal to SAT of phi. But how do you compute SAT of phi? That's why if we want a TFNP problem, then we switch to search SAT. And in the solution, you also need to come up with an assignment A proving that phi is satisfiable. I feel this is our natural problem, but turns out that we don't know if they have some, if they are seated in the TFNP hierarchy as we know. Even for this lower bound for majority, which is proved around 40 years ago, we don't have any idea on where it sits in the TFNP hierarchy. And for this search set problem, well, first, we don't know if it's total. And second, even if it's total, we have no idea. And actually, I lied a little bit here. Can anybody spot out the light? If no, then I'll spot it myself. Okay, the lie is that there is actually an efficient randomized algorithm for the majority refuter problem. For the search set one, under good assumptions, there are also randomized algorithms. So at least for these two problems, you really want to consider the class TF-ZPP, which is like total search problems first in TF-NP and second solvable by randomized algorithm. This class has not been systematically studied until our recent paper, I think, as far as I know. And unfortunately, our recent paper also didn't contain any insight on these two problems particularly. It does have some other problems. So I would say the complexity status of these two problems are completely unknown. Should I say that? And like,
The thing is with believed assumptions, right?
yeah. So I actually want to throw out this question. I have a problem in TF-ZPP. How do we talk about its hardness? How do we say that it's hard to provably de-randomize it into polytime? Okay, we have assumptions, but the assumptions also appear hard to prove. So is there any good way of talking about how hard it is for a problem in TF-ZPP?
Sorry.
Mm.
We believe that like I don't know, random planted set or something, it's hard to find the assignment.
Mm-hmm.
So that means that under this belief, search set is in TF-ZPP.
Yes.
Okay, but this is a belief. So if we
So I guess
how does
it's
this kind of fall into your framework there?
actually I feel there's no good framework yet for talking about TF-ZPP problems. Somewhat fortunately, the one-tip twin machine lower bound we'll talk about is complete for a class that we don't believe to be in TF-ZPP. So we can talk about hardness there. And this is also the same for the proof complexity thing I'll talk about next week. But for these problems, I really don't think we have good frameworks for talking about them. So I think they need a lot of further research, and I don't have really good things to say, except that I want to throw out these open problems to you. And then let's go back to TFNP and let me tell you the main course that we'll talk about. This is also a classic term in lower bounds. It says that one-tip Turing machine requires omega n squared time to recognize the language of palindromes. How many of you know how the lower bound is proved? That's good. So I'll need to cook the main course slowly later. But anyway, there's this lower bound, and there's also the fact that which we call the weak pigeonhole principle. It says that if I have a function that have n bits input and shrinks it to n-1 bits, then it cannot be injective. There has to be collisions of this function. Turns out that this theorem is just this fact in disguise, and this was proved by Lizzie, Zatu, and Igor. you can state the refutal problems for this theorem. The input is a one-tip Turing machine running in, let's say, subquadratic time, and it claims to solve the palindromes. And the output is an instance X, such that the one-tip Turing machine fails to solve palindrome on this instance. And there's a small technical caveat here that if we really want PWPP completeness, then we want to equip the Turing machine with a small advice tape. And your input would be the description of a Turing machine and the small advice tape.
Sorry, what is PWPP?
Okay, it's perhaps I should have used the pigeonhole principle first because I still need to introduce this class. Is the class of problems reducible to polynomial time weak pigeonhole principle. And you can just think of it as the following computational problem. Given a circuit from n bits to n minus 1 bits, you want to find a collision. We believe this problem is hard, right? In cryptography, we have this notion called collision-resistant hash function. And if a collision-resistant hash function exists, then this is hard. And the main result, not the only result, but like this result in Li Zhe Igor's paper that I'll talk about is that you can also interpret it as this refutal problem, it's PWPP complete. So there is a reduction from the refutal problem to PWPP, and there's a reduction back. Okay, so this is the main meat that I will talk about in the second half. Any questions so far?
Do we worry about this bits of non-uniformity? I mean, like a different statement than what you really would want, or?
Well, in their paper, they actually showed that the theorem is equivalent to some uniform version of weak pigeonhole principle, where I think that's just a technicality, or in the standard definition of Turing machine, the whole description should be a constant. So you can only reduce refutal problems where you have a constant input length to uniform versions of, I don't know, PWPP or something else. And if you want full PWPP completeness, then you will need to add some non-uniformity into your input. But I think that's just a technicality. For example, the lower bound that one-tip Turing machine with n to epsilon bit non-uniformity and subquadratic time cannot decide palindrome, this is essentially the same proof as the original lower bound.
This is trying to connect this to the beginning of the talk. Am I supposed to understand from this equivalence that if you have a proof system where you cannot prove the pigeonhole principle, you will not be able to prove also the theorem of Turing machine?
Yes, at least for the nice proof systems. And I guess you mean the weak pigeonhole principle.
Yeah, I mean the one that's. Sorry.
Yeah, so basically for nice proof systems, the probability of these two are equivalent. Like it can implement the reductions here.
So the way the proof goes is you study this refutal problem and show it's equivalent to this weak pigeonhole principle, and then you interpret this refutal problem as the theorem, and you interpret this weak pigeonhole principle as a fact.
Actually, the way that they did it is they just studied the equivalence in bounded arithmetic. For example, in the base theory, PV, polynomial time reasoning, they can prove the theorem from the fact and prove the fact from the theorem. But
And the and the way this two-way goes is through this two computational problem.
I would say that I interpreted the results as the PWPP completeness result.
That's your interpretation.
Another question. Suppose I didn't know the theorem on the left, but knowing this equivalence in would have also given you this theorem.
Yeah, actually, if you want to reduce the refutal problem to PWPP, what you do is you basically follow the proof of this lower bound. And the interesting reverse mathematics part is to reduce PWPP back to the refutal problem. Okay.
Wait,
Oh, sorry.
why is one of them reverse mathematics and the other not?
Oh, to reduce the refutal problem to PWPP, you just kind of implement the lower bound, follow the lower bound. And you observe that, you observe that the lower bound uses the weak pigeonhole principle. The reverse mathematics part is you want to show that the weak pigeonhole principle is necessary for your lower bound. So you try to prove the weak pigeonhole principle from the lower bound, which is like try to reduce PWPP to this refutal problem. And and here is the long answer on how to talk about provability and reverse mathematics. The answer is to go back to logic. So how many of you know what is piano arithmetic?
Good to be reminded.
Yeah. Basically, it's you have a language for talking about integers, which consists of zero, successor, addition, multiplication, and equality. And you have some very basic axioms describing how successors, addition, multiplication should work. And then you have this induction schema or our formulas phi. The induction schema just says, if I have a formula phi is true on 0. And if phi is true on x, then phi is true on the successor of x. Then phi is true on every integer or natural number. For now, we should really think the first 6 axioms are as not so interesting. Like it doesn't bring you much power of piano arithmetic, and the power comes from induction schema. So if you are a complexity theorist, then a natural question to ask is, what happens if you just restrict the induction schema to polynomial time phi? And I need to clarify a few things. The first is that we will treat integers as strings. You just fix some bijection. Actually, I shouldn't have used this because this only includes like strings starting from 1, but you get the point. So you need to fix some canonical bijection between integers and strings, and then integer n can be represented by around log n bits. And the second caveat, which I'll mention, but I don't want to go into details, is that you need to talk about polynomial time. So you need to enrich your language. For example, you need to add this floor x over 2, and this is not absolute value of x, this is bit length of x. So something close to log x. And if you have this 2, then you can talk about linear time and linear time hierarchy, the linear time of version of pH.
Number Y?
That's the so-called, sorry?
Concatenation?
No, that's something called, that's something that allows you to get polynomial time. The essential usage of that is it takes inputs to like n-bit strings and produces an n-square bit string. So with this symbol, you are able to talk about polynomial time.
Like the outer product of the system?
Um,
No.
I think the only thing that matters is the length of the strings. Mm. Mm. Mm-hmm.
Will you define what it means for a formula to run over time? It just means you take all the formulas that there is in a Turing machine. And if that's the case, then you can just take them. You don't need to enrich your life. Like you also want to
Mm-hmm.
argue.
I think taking all Turing machines was the approach taken by Cook, but I'm using the approach taken by Bass. You can build all polynomial time formulas using these things. And actually, I don't know the details of how you build them.
So what you're saying is
Mm.
that you don't want to restrict your axioms out of nothing. You want to tell us how you restrict the axioms, like in a constructive way.
Mm.
And that's why you're using these extra.
So just think of them as some language that allows you to talk about polynomial time formulas phi, or more precisely, formulas that are obviously polynomial time. Mm. Mm.
Initially, I thought
Mm-hmm.
formula is given by, and you can see its size but just by looking at it.
For example, if I have something like like a phi of a theorem, there exists a proof such that this is a proof of the theorem.
Phi is allowed to have quantifiers.
Yeah, then this is equivalent to halting problem, I think.
Right.
And now you need you need to only use quantifiers of the form like there exists x at most something, or for all x at most something. And this is the word bounded in bounded arithmetic.
And there exists x of at most n bits. Is that allowed?
Not if n is just a number, not a so-called length.
It's only allowed for length.
Mm.
The only exponential in log n.
Mm.
Or
Oh, I see. But you can.
Mm.
That's why you need these. Like that's why you need to divide by 2 and to
Mm-hmm.
division and
Mm.
take the absolute value so you can.
Not absolute value, but billions. Mm.
Sorry, not yeah.
Mm-hmm.
Yeah.
I'm sorry.
Mm-hmm.
Do you want to, okay. What does it mean exactly now? Formula has polynomial.
Maybe it's easier to talk about the polynomial hierarchy. Then it's like you can have, I don't know if I can write it here. For example, phi of x is equal to, I don't know, maybe there exists x1 less or equal to some term of x. You build terms from this language so that the length of this term will be polynomial in the length of x. And that will give you a polynomial bounded existential quantifier.
Is x1?
Huh? Some new variable. And let's say for x2 and so on. And finally, there's something, I don't know. There's some predicate, I would say. So you can build a polynomial hierarchy using this thing.
You say term of x. This is
Mhm.
just like when you say term of x to be like a polynomial, its length to be polynomially bounded. This I don't understand. Term of x to be.
There's some precise definition which I don't want to go into, but
Reset can it be a 3CNF?
Not 3CNF, I guess.
What's preventing it from being a 3CNF?
Oh, sorry. You want what to be a 3CNF?
Want to understand if phi encodes all of NP or no? Like when it says exist, x1 to xn.
Okay, for example, phi of a x, think of x as a 3CNF, and you can say there exists y less than tx. Let's say this is the input length n of the 3CNF, and I think you can compute it such that x, y. So this means that if x is a 3CNF and y is a satisfying assignment, and y is an assignment, then y satisfies x. You can express things like this.
I mean, okay, if we didn't have these bounded quantifiers, what I would have understood is like, right, in logic, like you can always encode integers into, I mean, into 3CNFs and assignments, and then write out an explicit formula that.
But the size of the formula will be proportional to the runtime.
That's fine. But my problem is your formula, it accepts, I mean, it has all sorts of variables, right? And then you can put integers in there and it computes something. Like, right, it's either 0 or 1. But if you can write this formula down, and it has a size, right? Constant size. And then you just put the integers in. So are you talking about like size in terms of when I put the integers in it, how much the length grows is like there?
Sorry, I guess I still didn't really understand your question.
My question is this. Phi is just a formula. Right? Whatever is written there, you can just translate it into like a string of a certain length that's like it's a legal form. Right? So what I don't understand is what you mean by bounded quantifier for polynomial time or something. There's something that I inherited. I think I'm missing here. Like why is phi x equals something? This is not just a formula of like 200.
Yeah, this is a constant size formula. Just like a Turing machine has constant size description, something like that.
Exactly. And now I want to say something about running in polynomial time.
Yeah.
And like I don't understand what this means precisely. So one thing you can say, I understand that you don't want to say, but I just take all these formulas such that I can compute them in polynomial time, and this is like my abstract set, and I'm only using axioms that come from this set. And you wanted to say something else, right? You wanted to say like all formulas where like you have this other notion of like
I guess I actually only want to say that there is some way to express all the polynomial time or pH concepts in this language. And to be honest, I'm not super sure about the details.
But if the point is that you can evaluate this syntactically, looking at the semantics of the formula. Like I can just.
Yes. For example, if you only use bounded quantifiers, there's no things like there exists x. There's only things like there exists x at most something. Then, and if the formula is constant size, then it describes something in polynomial hierarchy. This is syntactic.
Okay. So this is what I should take as polynomial. And I see, and it's positioned in the higher, like, and it's probably that if you have like these types of expressions, then they're in the polynomial hierarchy, depending on like the number of points. Okay.
I hope that like clarifies some confusions, but I guess what I really want to say is just that you just need to do some dirty operations, and then you can talk about polynomial time here. So you can consider, for example, induction schema or polynomial time formulas. And like, why should we only consider induction? It also makes sense to consider something else, right? So let's consider minimization schema or polytime phi. The minimization schema says that if I have a formula phi and it's true on some point A, then there's a smallest point x such that phi x is true, but it's never true below x. Now my question is, I have these two schemas both over polytime formulas. Are they equivalent? And which one is stronger?
While A imply.
I'll make sure that you understand this. If you don't, ask questions.
So ignoring polynomial time, like induction and this principle are equivalent, right?
So phi will only, like in the minimization scheme, phi will only have just one.
Oh, just one what?
Like it will only have wait,
Can you say more about why you're confused?
The stable phi will only have exactly one.
That's not necessary. It might have a lot of ones, and you are only granted that phi is one at the point A, but then the axiom says that there exists the minimal x, so that phi is one at x, but not below.
Oh, I see. So from that one and beyond.
Can you spell out why they're equivalent in not in polynomial time formula?
Yes, but maybe next slide. This slide I just want you to at least guess which one is more powerful.
I guess minimization is more powerful. So we need to go over. Okay, that's my guess. So if the formula has alternating 0, 1,
Yeah.
what would that look like? Because it would not be covered by induction.
Okay, maybe I should tell you the answer. If you want to know how powerful is induction, you can rewrite it into this form. If I have phi 0 and not phi a, then there has to be a place x where phi x is true, but phi x plus 1 is false. And then given an existential quantifier, you can look at like how hard is it to find the thing asserted by the existential quantifier. For example, here the x can be found actually in polynomial time, right? Polynomial in the bit length of a. Because we can do binary search, we know that phi 0 is true, phi a is false. And let's look at the middle point, like phi a over 2. If phi a over 2 is true, then let's look at the right interval, a over 2 to a. And if a over 2 is false, then we can look at the left interval, 0 to a over 2. And in time polynomial in the bit length of a, you can find such an x. But for the minimization principle, this search problem turns out to be P to NP complete. The problem is essentially I give you a satisfiable circuit, and I want you to find the lexicographically smallest satisfying assignment, and that's P to NP complete. So you can informally say that the minimization over polytime is like P to NP reasoning, and induction over polytime is like polytime reasoning. You can at least informally say that.
That's going back to your refuter.
Kind of.
Finding the same or?
Yeah, I think I treat them as the same thing. Here are some more chaos that I want to give to you. So we have minimization or polytime. It doesn't need to be polytime. What about induction schema over all NP formulas? Um,
So we should read polytime as polynomial hierarchy?
just polytime. Assume there's a good way of describing that.
I see. Even though it isn't exact.
Which of these two are more powerful, do you think?
They're equivalent.
Yeah. Any reason?
Well, I mean, the minimization, it's really to be able to compute. Right? Okay, I need to think.
Actually, I can formally give you the proof that they're equivalent if you think they are time. Or if there are no time, then I'll just skip that.
I don't know what you have in store.
Huh?
You only have 90 minutes, right?
Oh,
Just kidding, I'm just kidding.
give me more 90 minutes.
Okay, sure. You don't.
Do you want me to like go through the proof or at least one direction? So, let's say how to derive the minimization principle from induction for NP. Let's say that you have some phi, which is I'll just informally say that it's in polytime. And the minimization is saying, if I have phi of A, then there exists X. Phi X and not phi Y for Y less than X. And so let's just define the formula of say X to be there exists Y at most A minus X such that phi Y. And you do induction on psi. First, you can see that psi A or no, psi 0 is true, right? Because phi A is true. And then you can see that psi A plus 1 is false because there's no Y less than 0 or at most minus 1. There's just no such Y. Therefore, there must exist some Z such that psi but not psi plus 1. And you just take X to be, I think, A minus Z. And you prove the minimization principle. You can think of it as some reduction from the search problem defined by this to search problem defined by this. The next more chaos I want to go through more quickly. We don't need to use induction or minimization. We can also consider other principles. For example, what about the pigeonhole principle? Turns out that at least in the right-wise setting, pigeonhole principle and the induction or NP are incomparable, at least in the right-wise setting. If you are familiar with TFNP, then this is saying PPP and PLS are incomparable. And we don't even need to consider well-known principles. What about using lower bounds for majority as an axiom or principle? Something like that. And I guess you recover that this is really at least similar to comparing the computational complexity of search problems. And for example, for now, let's restrict on for all existing axioms. You can also discuss like for all exists for all or with more alternations. But for today, let's just restrict it on this on for all exists. If you have two axioms or two theorems or whatever, and you want to compare them for all exists, then you can write down the total search problems corresponding to those for all exist sentences. And you look at whether there are reductions between these two. Turns out that if axiom 1 is implied by axiom 2, then total search problem 1 reduces to total search problem 2. Also, the notion of reduction it depends on the notion of implied by.
Like, if, for example, in like the previous example, in innovation and reduction, basically just follow this proof that you written down on the board, and you like construct this reduction based on the proof. And like the power you need to implement by the reduction is like the power that's given by this
by the base system,
yeah.
And in fact, there's a converse direction, but you will need a strong base theory, so-called universal sentences in PV. The reason is that maybe some reductions are hard to prove, but our reductions are universal sentences. Like for every x, this is a reduction on input x. So if you just simply add all these universal sentences into your base theory whenever they are true, then the notion of reduction and the notion of implication becomes exactly equivalent. PV plus all the true universal sentences.
What is PV?
I didn't have time to define it for the time reason. You just think of it as a weak base theory.
You want to take a break soon?
Of course, and I think after the break we'll go through the reversal for one-tip two-machine load bounds.
Do you know that it's strong base theory is necessary? Could it be that all reductions you can put them?
I don't think so. I would guess you can cook up strange examples where a reduction is true, but it's hard to prove. So,
what I mean is that can you
but for the natural examples,
saying that this reduction is need to PV or
I'm not sure if I know that. By the way, I think for natural reductions that like appears in daily life, the PV without the universal sentences are really enough.
So I should think of these two facts as some kind of NP-complete reduction.
Maybe not. Maybe just saying computational complexity of refuter problems. It's really what you should look at.
But to prove these two facts, do you open box the proof of axiom 1 and axiom, for example,
No, you just need to like implement for example, implement the reduction in the theory, or implement the implication as a reduction.
So it's like an oracle. Like I treat axiom 1 as something you prove.
Yeah.
Open the box.
Yeah.
And then if I can derive theorem 2 or axiom 2, then I can turn this proof into a reduction for the total search problem 1, total search problem 2.
So that is a fact, or is that a theorem?
I would say a fact.
You don't know why this.
Oh.
Yeah, I mean, didn't we start the talk? You had two things are equal. One is the refuter, and one is you had some word called theory. And you told us you'll later tell us about that. Is that this notion of a theory? So we still haven't
what do you mean?
kind of seen why looking at the refuter problems is the right thing.
Let me say it in this way. If you are willing to use this as a base theory, then provability is equivalent to like reducibility among refuter problems.
You're saying it. Right, I mean, why do you believe you have a proof for it? Then it's a theorem. Okay, but you're not gonna show it.
But that's the part that I don't know why it's.
Oh, you mean you don't know why this is a fact, not a theorem?
Yeah, like why is it obvious?
Yeah,
Okay. I don't know how to explain why this is obvious.
you think it's obvious.
Kind of.
It would be nice for us to see it, but
Why this doesn't, for example, suffer from this red blinding barrier, right? Because we're treating the proof of axiom 1 as a black box and getting axiom 2. So for example, if I replace axiom 1 by like NP not in P poly and axiom 2 by P not equal to NP. So are you seeing black box?
Like you only need to consider the reduction, right? For example, you only need to consider the proof that axiom 1 is implied by axiom 2. Maybe axiom 1 or axiom 2, both of them are hard to prove in some sense. But if the implication is easy, then
So you are saying the implication does not suffer from this red blinding barrier.
I'm not sure how relativization barrier is relevant here.
you're imagining that the implication treats the axiom as black boxes. So
Oh, maybe this is containing the word implied by.
Yeah.
Like it's using very weak stuff, just like you do the NP convenience reduction.
Yeah.
Like I did the reduction stuff, and as long as you just use that, then it preserves the convenience.
Yeah, is that what you mean?
I think so.
Maybe then it's not that surprising.
Shall we take a break? So let's start. I guess first we need to know about how the lower bound is proved in order to reduce the refutal problem to PWPP, to the weak pigeonhole principle.
Remind us or show us how to prove that palindrome needs
Yes.
time on the one with change.
Yes. So theorem. Is this size okay? Sounds good. One tape to machine requires omega n square time to decide palindrome. And the proof is basically 2 steps. The first step is to reduce it to a communication lower bound, namely that if I have 2 parties, Alice and Bob, deciding whether their secret strings are equal, then they need to communicate omega n bits deterministically. And the second part is to prove the communication lower bound. So the first part is that suppose we have a one-tape Turing machine that decides palindrome. Let's say that Alice and Bob has secret strings x and y. Both of them are length n. Then we can just put them together as an input of a palindrome. Here, since we need to decide whether x is equal to y, we reverse y here and use this as reverse of y. And let's just fill in some zeros on the middle. The goal is to make any one-tip twin machine if the tip head moves from x to y, then it should need n steps. So at least informally speaking, this one-tip twin machine, if it wants to cross this middle thing n times, then it will require n squared time. And suppose we have a one-tip twin machine of time complexity less than n squared that decides palindrome, then Alice and Bob, the idea is Alice and Bob simulates the twin machine together. And whenever the head goes from x to y, or goes from y to x, Alice sends some message to Bob, or Bob sends some message to Alice. To exactly implement this, we will need to fix some index I such that the head will only cross I like at most little or n time. First, for every input, such an I exists by like a counting argument. And it's actually an easy counting argument provable in like easy reasoning, because there are just like n many elements, and you are just saying their sum is less than n squared. Therefore, one of them is less than n. And as a communication protocol, we want Alice and Bob to agree on some I. So what they do is Alice computes the smallest I, such that Alice computes the smallest I on input x 0 to the n and the reverse of x. Let's define I of x is smallest I mean I is among this part. Cross like at most, let's say little o n. Let's say there is some way to fix the constant here, but I don't really want to care about that. Cross at most little o n time on input x and 0 and the reverse of x. Then the first step is Alice sends I of x to Bob. Bob sends I of y to Alice. And if these two indices agree, then they agree. Otherwise, they just say they are not equal. Okay, and then now then we agree with some I, and we can say that anything on the left of I, Alice will care about it. Anything on the right of I, Bob cares about it. And and they can just simulate the Turing machine. And whenever the head goes through I, let's say from left to right, Alice sends the current state of the Turing machine to Bob. And this will allow Bob to simulate the Turing machine on his own until the head crosses I again, and Bob can send the current Turing machine state to Alice, and so on until it ends. So what should I write here? Should I write something formal? Sounds good. And of course, they need to stop when the Turing machine halts or the Turing machine runs in like enough number of steps. And if the Turing machine decides that x 0 to the n reverse of y is a palindrome, then x is equal to y. Otherwise, x is not equal to y. So this means that if I have a one-tip Turing machine deciding palindrome in like subquadratic time, then I get a sublinear communication protocol for equality. This part is fine. And the second part is to prove the communication lower bound. Suppose that I have Alice and Bob who are solving the equality problem using communication, and the communication is, let's say, less than n bits. Then we can do the following experiment. We can first send. Okay, let me say it in this way. Let's say f of x is equal to the communication transcript of when I give both x to Alice and Bob. And if the communication protocol only uses, let's say, less than n bits, then fx is some function from n bits to less than n bits. And by the weak pigeonhole principle, there is a collision. There is a collision, which means there is x1 not equal to x2, such that fx1 is equal to fx2. And now, let's consider what happens. Okay, first, both fx1 and fx2 should be accepting, because both of them are transcripts when I give the same input to Alice and Bob. However, what happens if I give Alice x1 and Bob x2? What happens is that, let's say Alice speaks first. Then the first message is whatever Alice said in fx1. And since fx1 is equal to fx2, Bob will receive the same first message as in x2, and Bob will say something like the second message in fx2. And on Alice's side, it is always equivalent to where Bob has x1. In Bob's side, it's always equivalent to when Alice has x2. Therefore, the transcript when Alice gets x1 and Bob gets x2 should also be equal to these things. But these things are accepting, and x1 is not equal to x2. Therefore, the protocol has to fail on x1, x2. And that's the lower bound. Now let's see. I guess it should be easy to reduce the refutable problem to a weak pigeonhole principle, but let's just work out that. Reduces, I think actually mapping reduces to the weak pigeonhole principle. Maybe I should just write PWPP. So our input.
The difference between PWPP and this WPHP.
I think that's the same thing with different name. WPHP means weak pigeonhole principle, and the PWPP means a complexity class based on the weak pigeonhole principle. Okay, so our input is a one tape. Should I write the full name here? Okay. Okay, the input is a one-tape Turing machine. Let's call it M. And suppose it has a clock that makes it run in subquadratic time. Let's say n to 1.9. And the output is some string. x such that mx is not equal to the palindrome x. And what we do is let's define fx to be equal to the transcript outputted here. So it's oh, this is a different x. Maybe I should use w, because what will happen is that I'll define some n-bit string x, and w will be of the form x0 to the n and the reverse of x, or x1 0 to the n reverse of x2. So given an n-bit string x, let's define fx to be the transcript outputted in this communication protocol. In particular, it consists of ix, which is log n bits, and I'll use this for concatenation, and communication of Alice and Bob. Actually, what this means is just a sequence of twin machine states whenever the head crosses ix.
X and X for both Alice and Bob.
Oh, yes. Let me write it in this way. So this is actually what you get when you run the twin machine on x 0 to the n and the reverse of x. Then, this is the reduction to the PWPP problem. So we need to solve PWPP on this function f. But after solving f, we need to translate the answer of PWPP into an answer to the refuter problem. So note that this is n bits input, and this is something less than n bits, maybe. And after solving this, so PWPP gives us two inputs x1, x2, such that fx1 is equal to fx2. And now the claim is that the twin machine will make mistake on either x1 0 to the n reverse of x1, or x1 or x2 0 to the n reverse x2, or x1 0 to the n reverse x2. The reason is that if the twin machine is correct on both these two inputs, then the twin machine should output both of them are palindromes. But then by the same reasoning as here, the twin machine should also output palindrome on this input. So the twin machine is incorrect here. To summarize, the reduction is just something like input a twin machine, and I'll define a function f from n bits to ix and the communication transcript, and then given a solution of PWPP, you just make these three inputs and test on each of them whether the twin machine is correct or not. And the proof guarantees that one of them has to be an incorrect instance. So that's the reduction from the refuter problem to PWPP. And maybe the interesting thing is the converse. How do you reduce PWPP to refuter problem? Should I erase something?
I have another board.
Oh, wait. Oh, this board.
Not all the way through, so maybe draw a line. Can you see it over there?
Actually, no.
I think this.
Is this okay?
Yeah,
you can go a bit above that.
Oh, that's okay. I think it's like approximately equal. Okay, so now we want to reduce PWPP to the refuter problem.
That's enough thing from you.
Mm.
How, what are inputs to?
Oh, I'm going to write that down now. The input is some circuit C. I'm making my life harder here because C only shrinks its input by 1 bit. But soon we will see that this is kind of, well, this is equivalent to C shrinking its input to length n to epsilon. And we want to find a collision. This is the definition of PWPP complete problem. What should you do if you want to reduce PWPP to some total search problem? The answer is that you can imagine that you live in a bizarre world where there's a bizarre function called C that is a perfect hash function. So it shrinks its input bit by 1 bit, but somehow there's no collision in C. So you can think of it as an axiom, although the axiom is false. For any x1 not equal to x2, cx1 is also not equal to cx2. So you live in a bizarre world with such an axiom. And the goal is to come up with a one-tip Turing machine that runs in, actually I can make it runs in n to 1 plus epsilon time and decides palindrome. Is this clear so far? And what you can do is, suppose you can analyze your Turing machine in this bizarre world, then you just analyze it as the same in the normal world. The analysis will give you either the Turing machine is correct or the axiom is violated. Actually, for every input x, the analysis will give you either the Turing machine is correct on input x, or some related x1, x2 violates the axiom, and x1, x2 will be easily computable from x. So our goal is to, like under this bizarre axiom, we want a one-tip Turing machine. I can do it in arbitrarily close to linear time. Deciding palindrome. Any idea on how you should do this? Well, the obvious idea is to just apply this compression function, right? And if the compression function gives you the same hash, or like you split the input into half, if the hash of this is equal to the hash of reverse of this, then you just accept that that this is a palindrome. And the problem with this approach is that C is just an arbitrary circuit. It's unclear how to evaluate C in one-tip Turing machine n to the 1 plus epsilon time. But you can do some classical tricks in cryptography. Suppose that you have a long string, let's say of length capital N. I'll set the parameter later. And C is only size small n. Then what you can do is you can define the hash of this very long string to be, you first hash the first little n bits, and this will give you a string with length capital N minus 1, where the first bits are replaced by the hash. Then you hash this little n bits. You get a string of length, again, slightly smaller. And you hash the length little n prefix again, and so on. You can do this all the way down until the length becomes little n, actually little n minus 1. Then you output the final length little n minus 1 digest as the hash of the string. And you can see that this is implementable by a one-tip twin machine quite efficiently. Actually, it's in linear time in capital N times some unspecified polynomial which depends on C, let's say little n to the some constant C. So what we get is that you can evaluate the hash length little n minus 1 hash of this length capital N string, very long string, in this many time. And you can just set capital N to be large enough so that this is at most capital N to the 1.01. Then our one-tip twin machine is simple. It first, it has an input. Okay, our one-tip twin machine, it has an input and it needs to decide whether it's a palindrome. It first tries to split the input into two halves. By some tricks, you can implement this in one-tip twin machine near linear time. So that you can recognize this is the middle point. And then you just run the hashing algorithm. You first get the first little n bits and replace it with its hash. Then you get the first n bits again, replace it with its hash, and so on. You can compute the hash. Okay, maybe I should write it somewhere here. So you can compute the hash of let's say you compute the hash of the first half and the hash of reverse of the second half. And you just output whether the hashes are equal. So this produces the one-tip twin machine, and you can fit this into your refuter problem. But we still need to see how to solve PWPP. So how to find the outputs x1 and x2 given some input where this machine is incorrect. So we are given some W such that our machine W is not equal to palindrome of W. First, let's consider this task. Suppose we are given two strings, each of length capital N, and the two strings are different, but their hash are the same. we want to find a small string of length little n such that the two small strings are different, but they have the same hash. What we can do is we can just do the same construction of how we build a large hash from small hash. For example, let's look at the first things, and maybe I can say it in this way, like during the computation of the large hash, we'll have a lot of intermediate strings, right? For example, the second one has length 1 bit less than this one, and the third one has length 2 bit less than this one, and so on until we have the final hash of length little n. And this is true for both computation. Okay, maybe I didn't need to erase this part. I don't know. And these two are different input strings, but their hash are the same. So there's some place where they start to become different. Let's say maybe this string is equal to this string, but this string is different from this string. What you can see immediately is that this prefix and this prefix are different, but they hash to the same string. So we have solved the following problem. Given a collision of the big hash, find a collision of the small hash. Then we are given some string such that M fails to compute palindrome on this string. This string will be split into half, and M will output whether the hash of the first half is equal to hash of the reverse of second half. If the string is in fact a palindrome, then M will output it is a palindrome. So the string has to be a non-palindrome. And this means that the first half and the reverse of second half are different, but they have the same hash. We can use the previous procedure to find some hash, to find a collision of the small circuit C. And how am I doing on time?
12:30. What else do you? And this completes the reduction.
Yeah, I think I rushed it. I don't know.
I think it was very clear.
And I was planning that if I still have time, I'll go into Oliver Colton's paper. I have some, but if we don't have time, then we don't really need to do that.
So what other things were you planning?
So Oliver Colton had this result that he had some program called lossy code. If you don't know what that is, it's just some other kind of weak pigeonhole principle. And it can be solved in randomized polynomial time. So he was interested in de-randomizing lossy code. He had the result that if you have a function computable in some exponential time bound t on randomized machine, but hard for t to the 1 plus epsilon time on one tip 2 machine, even with space limits, then you can use this hard function to de-randomize lossy code. And he called his paper de-randomization from time-space trade-offs. But I just want to talk about some, like, you can say it's my interpretation of his result, that his result is actually saying that lossy code reduces to the refuter problem for one-tape twin machine versus random access machine. You can consider the lower bound saying if a one-tape twin machine wants to simulate random access twin machine, then it has to run in quadratic time. And you can also define the refuter problem for that lower bound. And what I didn't have time to go into is that Oliver's result is essentially a reduction from what he called lossy code to this refuter problem.
I have some questions for this. So I understand the proof and the reductions between refuter and this weak pigeonhole principle. But like, I'm just curious, viewing this as two computational problems, I understand their reduction. How do you like go between them? And I suppose this also gives a proof for the two theorems that defines these two class of these two functions, these two computational tasks. So if I have the reduction, but I only know one statement, for example, I know this weak pigeonhole principle, and then using this proof, I can also know that one tape Turing machine must need quadratic time to decide palindrome. Is that how I should think of it, or are you trying to tell us something else?
I guess I really want to emphasize the reversal that, well, you can interpret the reversal as the weak pigeonhole principle is necessary for proving this one-tape twin machine lower bound against palindromes.
In the sense that the computational problem of these two are equivalent.
I think it's also in the sense of like those two facts, like because you have this reduction, and it's you can prove a theorem about like palindrome, based on your axiom, you're also supposed to derive from this a proof for the pigeonhole principle. This is what this is how this connects to the previous hour, right?
This is like based on the lower bound for palindrome, you can derive the weak pigeonhole principle, right?
Maybe the two theorems at the beginning was like kind of simple. But somehow I view this reduction as saying your proof at the beginning can be made into an algorithm.
What do you mean precisely?
Like at first you presented the proof of the palindrome results.
Palindrome lower bound.
And, that's a proof. And this is turning the proof into an algorithm.
An algorithm for what?
An algorithm for solving the, like to find the witness, assuming you can find the witness of the weak pigeonhole principle.
Yeah, the first part you can.
Yeah, that one is saying you can turn a proof of weak pigeonhole principle into an algorithm that finds a collision. Assuming you can find.
No, no, we are not assuming a proof of weak pigeonhole principle in the reversal. We are proving the weak pigeonhole principle from the lower bound.
Even more, we're finding a collision for the weak pigeonhole principle.
Sorry, I'm still confused about what your question is.
Yeah, I guess my conclusion is this seems to be a proof that weak pigeonhole, assuming assuming the polynomial problem is convex, then weak pigeonhole principle is true.
Yeah.
And you just turn this, like you just write the proof as an algorithm, an
Yeah.
reduction.
Mm.
I guess my question is how, like, why do you want to make this perspective shift? Like, why don't you just view it as a proof?
You can also do that. In fact, the CRO paper did exactly that. I don't know if they mentioned like PWPP completeness, maybe, but their main perspective is proof theoretic.
And then this is just proving like two theorems are equivalent.
Yes.
Assuming this theorem, you derive the second
Yes.
theorem. Assuming this theorem, you derive this theorem. It's just
And
the
you're
way you,
algorithmizing.
yeah,
Yeah.
it's just the way you,
Yeah, I think it's fine to consider either the proof theoretic thing or the algorithmic thing. Like it's just like which one you are more used to.
so it is fair to say that like the reverse mathematics is just proving equivalence of the two theorems.
Oh, this is what it's meant to be. Like this theorem is equivalent to that axiom.
Oh, I see. So I should just group the theorem statements in clusters of equivalence. Although you want this equivalence to be proved using algorithms, reductions, or not necessary.
What do you mean by you want the thing to be proved by algorithms?
Because we're emphasizing this reduction, right?
There's a question here, but maybe we can take it.
Yeah.
Yeah.
Thanks so much for the wonderful lecture.
Thanks.